everyone. Thank you for joining me today. My name is Adam Drescher, and today I'm telling you about some work that I've done with my colleagues at Washington University in St. Louis, in particular, analyzing the performance of ICN forwarders on the wire. And why might we want to do this? Well, there are plenty of ICN papers out there that focus on forwarding performance and include some experimental analysis. However, few of those papers are focusing specifically on the evaluation methodology that we should consider for an ICN forwarder. And for those materials that do focus on such a thing, um, they're often missing some of the practical steps someone in the community might need in order to replicate that process on their own. And so we aim to remedy this. And the way that we're accomplishing this is by providing a series of behavioral microbenchmarks that we can apply to ICN forwarders that interrogate specific components of the forwarder and hopefully reveal subtle behaviors in its forwarding performance. And to show the efficacy of these micro benchmarks that we're providing, we've applied them to two well-known ICN forwarders in the community, um, Metis from the CCNx project and NFD from Named Data Networking. Uh, it's not to say that these two forwarders were chosen because they're the bleeding edge in performance, but just to show that we can reveal subtle conclusions about their performance with these experiments. We also detail our steps for our synthetic workload generation and other practical concerns for experimentation to allow others in the community to get up and running with a rigorous approach. And so we have a few key focuses for our micro benchmarks that we're providing. And the first and most important is that we want to probe the core data structures in an ICN forwarder because that's where the biggest difference in performance behavior will be. And so that is the PIT, fib, and content store. Another very important aspect is that if we're probing the PIT, we want to minimize the aspect or the influence that the fib and the content store have for the course of that experiment so that we can truly measure the effect of the PIT or whatever we're interrogating the PIT with. And so minimizing the other core structures so that you can focus on the structure you're investigating is important. And by doing these things, we can reveal some pretty subtle interactions without instrumenting the forwarder itself, only through end-to-end testing. And so first I want to talk a little bit about how do we do our synthetic workflow generation. And so Cisco publishes an umbrella top 1 million domain names sorted by the popularity of those domain names. And so we convert those domain names to a hierarchical ICN name. And that gives us structure with multiple name components already built in. And then we add padding to the end of that name in order to make it the average URL length, which I believe is 76 characters. Once we've developed this list of all of these padded converted ICN names, we now sample that with a zip distribution since they are still ranked with alpha values taken from a useful RFC, RFC 7945. And so just to show you a quick example of what this process will look like, if we take one of the top 20 results in the Cisco umbrella list, production server at Netflix, we can see how we can retain the hierarchical information with the top level domain, the actual domain name itself, and the subdomains provided, and convert that to a hierarchical ICN name. And then once we do that, we add the padding just like we said. Here I just have a placeholder with the padding because it would take up too much space. And those are the names that we're then sampling with the zip distribution to actually generate the workload that we use on the wire. And so now let's just dive into a couple of the micro benchmarks briefly. The first is targeting PIT scalability and the influence of interest lifetime. And so for this particular micro benchmark, it's interest forwarding only. There are no data packets coming back. And that's because you don't want data packets satisfying interest packets in the pit, and then that entry gets purged early. We want to stress the pit. We also focus on small packet forwarding rate for this because with large packets, bytes come pretty cheaply, and the per packet cost is really what we're after here. In order to minimize the fib, we use a default route, so that is having its lowest possible impact. And then for the content store, we disable it entirely. And so that's how we ensure that any differences in performance we might see should be related to the pit itself. And so I have on the right a plot of the performance results from both Metis and NFD. Sorry, with the picture-in-picture, the top right might be covered a little bit, but I can assure you that Metis's results are incredibly consistent no matter what the interest lifetime is. But anyway, on the x-axis, we have our actual measured value, the interest forwarding rate in thousands of packets per second. And then on our y-axis, we have the tested interest lifetime for those two forwarders in milliseconds, ranging from 1 at the smallest to 5,000 milliseconds at the largest. And we can see Metis is incredibly consistent across the entire range of interest lifetimes. And with NFD, we can see that it has a performance knee at a 5 millisecond or so interest lifetime, and then the performance decreases relatively aggressively as we keep increasing the interest lifetime. And this does have some interesting consequences if someone found themselves in a position where they needed a decent amount of packets per second out of NFD. Because the default interest lifetime is 4 seconds or 4,000 milliseconds. And you could be operating at a significantly lower forwarding rate than if your application allowed you to have a more tight interest lifetime. And so the PIP performance of NFD changes pretty substantially as the interest lifetime changes. For the second micro benchmark I'd like to show, we decided to focus on probing the content store. And in order to do this, instead of only doing an interest forwarding experiment, we're going to be doing full interest data exchange. And also, instead of doing small packets and looking at the forwarding rate in packets per second, we're using large packets and measuring the good put. And the reason for that is what better way to test the content store's efficiency than the benefit that you get if you're getting a high hit rate, and then you get a boost in good put. So that was the focus there. On the x-axis in the graph, we're plotting our measured value, which is the good put, as I said, measured in megabits per second. And then on the y-axis, we have the configurations that were tested, content store on and off for both Metis and NFD, and then for each of those, the zip alpha value of 0.64, which corresponds to about a 10% hit rate in the content store, or 0.84, which corresponds to about a 50% hit rate in the content store. And for Metis, if we focus on the content store off results, we can see it's relatively consistent. And then if we go to content store on with an alpha of 0.64, roughly 10% hit rate, we get a boost in our performance, a small one, but a boost, which is what you would expect if you're getting a 10% hit rate. Then for the 50% hit rate, which is the alpha value of 0.84, we get an even larger boost in good put. So those results are exactly like you would expect. For NFD, that is not the case. But first, let's start with the content store off results. That's pretty normal. Those are consistent. And then if we turn the content store on and look at the alpha value of 0.64, the 10% hit rate, our performance tanks tremendously. And that's because the cost of enabling the content store is too large of a cost. that even though we're getting 10% hit rate, we're taking a performance hit. And so that's around a 20 megabit per second difference in good put, just because we enabled the content store. Um, and these are almost 1,300 byte packets that it's serving. So it has the potential to significantly affect the good put in a positive way. But the next one is the alpha value of 0.84, and this is the real shocker. Even with a 50% hit rate, 50%, we still don't even break even on what it cost us to enable the content store, and we're actually getting less good put than the case where we just disable the content store entirely. Granted, the difference is smaller. It's a difference between 105 megabits per second and 109 megabits per second in the case where it's off. But you would still expect 50%. We should definitely be getting a boost in good put by enabling the content store, and that's not the case. For future work, improving the way that we distribute the names beyond just a standard zip alpha 0.64 or 0.84. You could also have separate distributions for the actual domains that we were using, and then a different distribution for the actual name of the content. We didn't really have a distribution for the content names. Those were just the padding values. And then adding new micro benchmarks and refining the ones that exist. These things are not set in stone. And I'm sure there are plenty more useful things that people can think of to measure and see interesting behaviors. And then what did we accomplish? Well, we specified the steps for our synthetic workload generation so other people can follow in our footsteps, going from sourcing the data to actually generating the data set that was used in the experiments. And we provided micro benchmarks that illustrated some pretty interesting forwarding behaviors in our example forwarders that we tested. And they focus on those core ICN data structures, and they definitely had a measurable impact. Well, thank you all for your time, and I'd be happy to take any questions.